All right. Thank you again for the invitation. This is a few times now, and we've been 7 years on Mars, so can't complain. Hope I get to come back many more years as well. It really is something to be a UCLA Bruin and have to walk through the USC homecoming. That was not fun. Curiosity, this is where we were this is now actually more than a year ago, but this is one of our self-portraits that we take with the camera at the end of the arm. We only realized sort of late in development that the camera that we put on the end of the arm to look at microscopic views of rocks actually was capable of focusing out to infinity, so we could take pictures of the landscape, and then it was only one step further to think we could look back at ourselves. It's a very narrow angle camera, so it actually takes 57 different frames to create this selfie, and then you kind of Photoshop it together and remove the arm. But nevertheless, it's kind of fun. Okay, so what I'm going to do is give a little bit of background on the mission, and then along with some more recent updates, and hopefully get that in and not extend your time into lunch too much. But this is this kind of sets the stage for what Curiosity went to go study, and also the nature of our landing site. So as everyone in this room is aware for sure, Mars, we believe pretty strongly nowadays that it went from wet to dry, and it may have also gone from warm to cold. We're less sure about that, but for sure, 3.5 to 4 billion years ago, Mars was wet and maybe warm in the period of time that the geologists call the Noachian, like Noah with the flood and all that. And then there's a Hesperian era where the climate changed dramatically from wet and possibly warm to beginning to get cold and dry. And then the Amazonian, which is really the major part of Mars history, the last 3 billion years, has all been this very cold and dry planet. And we decided to study the time period right here, the very interesting time period when Mars is going through that dramatic change. So Mars was once wet, and we'd like to understand if we can, from the geology we can see on the surface that's preserved from 3 billion years ago, was it warm also? And was it habitable? And this word habitable, that really describes the core of what this mission's all about. So what is habitability? Here's a place on Earth that we don't particularly think is that, it doesn't feel that habitable when you're there, Death Valley. But of course, it's an extremely habitable place on Earth, and if we found anywhere like this in ancient Mars, no reason to think life couldn't have made great use of it. So what is a habitable place? If you had to think of the broadest definition, it's a place that has persistent liquid water. We don't know of any form of life on Earth that can survive without liquid water, and you need the persistence to allow evolution and biology to have time to do its work. Key chemical ingredients of life. All life as we know it has some common denominators in terms of the building blocks, carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, organic molecules. We can look for all of these things in the ancient terrain of Mars to see if Mars had those building blocks that life could have used. And then energy for metabolism. We all need energy sources. Sunlight, of course, is one that helps power plants and things like that. There's also chemical sources of energy for microbes that live miles below the surface on Earth. They can survive far away from sunlight because they use the chemicals available within rocks and minerals. So we can look for all these things, and if we find a place on Mars that had all of these things simultaneously, we could call that a habitable environment. Doesn't mean that life ever existed there, and that's not something we can actually prove with Curiosity. We designed this mission and our payload to study the habitability. So it's really more of a geological rover, and the next one, Mars 2020, will focus more on the actual search for biology. So here's our rover, 6 wheels, car-sized. You're probably all familiar with it, but we have built this rover around the idea of having a big arm with a jackhammer drill at the end of it, so we could take samples of rocks, create a powder from those rocks, and deliver the powder to laboratories that are built into the front of the rover. And this is what's necessary to do that habitability experiment. To search for organic molecules, to search for carbon, we have to be able to sample rocks that date from 3 billion years ago and put them in these laboratories and look for those building blocks of life. And then the next question is, once you've designed the best rover to execute those science goals and the best payload to do that science, you still have to decide where to send it. And the real challenge is that Mars is a planet that's, as you all know, almost as big as Earth in the sense that you take all the land masses on Earth and you shove them together, removing the oceans. That's as much surface area that Mars has. So if you're thinking of, you have your one chance to send a rover with this incredibly valuable scientific payload, where's the one place to go on Mars where you can answer these questions? And so we scoured the planet for several years and chose a site called Gale Crater, which has this mountain in the middle of it called Mount Sharp. And Gale Crater was attractive because this mountain formed after the crater formed. It's not part of the crater in terms of sometimes craters have a peak from the rebound, but this is a mountain that formed later when sediment was delivered to the crater by either wind or water. And we had reason to believe that maybe it was water, and that's what made this an exciting place for potential habitability. We thought it might be water even before we got there because the mountain has layers in it. This is, of course, a picture we took once we landed. And the mountain has layers of different minerals. There's one that we call the Murray Formation that doesn't really have a distinct mineral signature from space. There's one that has iron oxides, this mineral hematite. There's a layer that we're in currently called the Claybearing Unit, which has a lot of clay minerals which form from the action of water and rock. And then there's a sulfate-bearing unit. These nice rounded hills are all made of layered, hydrated sulfates. So lots of reason to believe, even before we got there, that water was involved interacting with these rocks. And so the goal then, this offered us a chance to land a rover, climb the mountain, and have many, many years of opportunity to look for each of these layers, which just like if you were hiking the Grand Canyon, the layers on the bottom are older and the ones higher and higher are younger. So now you can see the attraction of this site where it offers not only many different environments to assess habitability, but a range of time periods too. This took tens of millions, hundreds of millions of years, or maybe 100 million years to form this mountain. And so it gave us the chance to look for any of those time periods, any of those environments for one that might be habitable. Okay, so here's a map of our traverse. Actually, we started much further out, but this is kind of the last year or so of our traverse, and then what's coming up in the future as well. As I mentioned, we're now in what's called the Claybearing Unit, which is this green-colored unit here behind this ridge. And we're exploring this Claybearing Unit, and in the next few years, we hope to climb into the sulfates, these rounded hills, and up this ancient river channel that carved a whole canyon through the sulfate unit. This is a picture that was taken by the HiRISE camera on the Mars Reconnaissance Orbiter. So from a couple hundred miles above us, we have this wonderful camera that's been mapping Mars for more than a decade now. And every once in a while snaps a picture of Gale Crater and sees the rover down there. So this is the ridge that's made of iron oxides, hematite, and this is the clay-bearing unit that we're exploring now. And last May, HiRISE got a picture of the rover. You can even see the mast here and the rover facing this way and its wheels from 200 miles away. So this is what it looks like inside the clay-bearing unit. It's very rubbly. So that was a surprise. We thought we might see a lot of bedrock that actually has all those clays that make the spectral signature that we see from space. But instead, the clay signature seems to be in a lot of these pebbles and occasional ridges. So we've been exploring these ridges, and we just drilled into one of these ridges and are now seeing what might be evidence of the beginning of that major climate transition from wet to dry, because the floor of this clay-bearing unit is rich in clay. Looks to be the same kind of rocks we've seen for a while now that formed at the bottom of ancient lakes and then solidified into rock, whereas these ridges seem to be more like wind-blown sand or something that might have represented a drier environment. But now I'm going to go back a little bit. That's kind of where we are now. A little bit more about some of the big highlights from the mission as a whole. This is a summary slide of our kind of earliest and biggest result of the first year of the mission. This is the first site we drilled in a place that we called Yellowknife Bay. This wasn't even on the mountain yet. This was in the flat area next to the mountain where we landed, and we saw a place, again from mapping from orbit, that looked like it might be one of these ancient lake deposits that we thought we'd explore. We drove there about 500 meters from where we landed, and we drilled into this rock and put the material into our 2 laboratories. And in a really brief sense, I'll tell you a little bit what these sophisticated labs do. These are real, kind of geologically state-of-the-art or state-of-the-practice instruments that we brought to Mars in a miniaturized form. One of them is called an X-ray diffractometer, and you shine an X-ray through that rock powder, and rocks are have crystalline minerals in them, and you form this diffraction pattern. It's like a rainbow prism that from light into glass. And geologists who do X-ray diffractometry can read the spacing and intensities of these rainbow layers, and can tell you what minerals are in there. And one of the things we found was that this scattering down here at low angles is from clay minerals, phyllosilicates. So this was confirmation, even though we kind of had hints from that from space, that this material, even out on the plains, was very rich in clay minerals. About 20% of the rock had turned, from the action of water, had turned from basaltic rock into clay. The other laboratory that we bring with us is a mass spectrometer gas chromatograph, another very basic instrument you'd find a few buildings down in the geological sciences lab here at USC. And what you do here is you put the material into a cup and heat up that cup, and as you heat up with temperature, different gases come off as the minerals and other material in the rock powder breaks down with increasing temperature. So a bunch of water comes off at low temperatures. This may be just adsorbed moisture in the ground. And then you get another peak of water out here at 600 or 700 degrees, which are the clay minerals themselves breaking down and releasing their water. So this allows us to have another independent confirmation from the mineralogy instrument. From this instrument, we can get a second indication that there was a lot of clay minerals. The other thing this found was a CO2 release, oxygen release, sulfur releases. We also saw nitrates, which are important nutrients for life. So those important chemical elements that I mentioned earlier, the carbon, the nitrogen, the oxygen, the sulfur, the phosphorus, all of that was found in this drill hole. So here we have, in the first year of the mission, we had found a place that geologically was consistent with an ancient lake bed, so persistent water. We had the key chemical elements, building blocks of life in all these different elements we found. And the third thing, if you remember, was energy sources for life. Of course, we would have had sunlight here, but we also have, interestingly, forms of sulfur that are both oxidized, SO2, and reduced, H2S, which to a chemist means that there's a chemical potential between them, energy source that life can use, like microbes do underground on Earth. So in the first year of the mission, even before we got to the mountain, we were able to say that we had found a habitable place on Mars, a place that if microbes were dropped there or evolved there 3 or 4 billion years ago, they would have been able to survive. When we got to the mountain, we found that the mountain itself was composed of finely layered mudstone, so rock that formed as mud, and the nature of these very fine layers and the overall geologic setting led to our geologists to interpret this as an ancient lake environment. So each of these layers was maybe a seasonal layer of influx of sediment into the lake that formed a very flat-lying layer at the bottom of the lake of mud. And then over time, as the layers were deposited successively year after year, those layers formed this big stack of rock. They hardened into rock, and then later erosion kind of carved away the side of it, leaving it exposed for us like a highway road cut. So that told us that the mountain itself had a lot of water involved in its formation, specifically a long-standing lake that rose and rose and rose in height as more layers of mud were placed on the bottom of it. But we also found that after everything I just mentioned happened, after the layers of mud formed, it turned into rock, the rock was then buried by even more layers and fractured, and then erosion happened and it fractured some more. After all that, there was still groundwater flowing through these rocks, as evidenced by these mineral veins. Each one of these are they're white calcium sulfate, like gypsum-like minerals that have filled in all the cracks in the rock as water flowed through the cracks and basically left what's similar to hard water deposits behind that filled in the cracks slowly. And as the softer mud has eroded away, those calcium sulfate minerals are now these little fins sticking out that are the shape of the cracks they once filled. And we found just a ton of these, especially below rocks that may have been a cap to the flow of groundwater, where the groundwater was trapped circulating here below this harder rock. We see a lot of these, what are called mineral veins in the rock. And importantly, the big picture conclusion is that not only were these lakes there for a long time, but after all that, groundwater continued to flow for many more millions of years, leading to these deposits. So this place was habitable for a long time. That's the bottom line. This is more of just a postcard. I just like the view. So here is, now we're actually climbing the mountain. This is the summit of the mountain here, but we're already on the shoulder of it. And there's multiple layers of rock on this mountain, as we mentioned, including some that formed after the mountain already took its shape. And these are layers of sandstone that were once a continuous sea of sand, like sand dunes, like this here was continuous with this. This was all buried under sand. And then eons of erosion have removed almost all of it, just leaving these towers, kind of like Monument Valley in Utah or Arizona, things you see like that, where there's a capping sandstone protecting this tower of softer rock beneath it. One of the things we found in the last couple of years is that, as I mentioned, we're starting to see evidence that the lakes didn't last forever. As we've gone higher, we started to see evidence that the lakes may have shrunk and grew in different climate patterns in the ancient past. And this is evidence for one of those things. This is a rock where we found one of those layers of mud actually formed cracks in it. Just like a lake bed does on Earth, when it dries up and that layer of mud is exposed to the sun, it can dry up and crack. And these mud cracks are just the kind of shape, and you can measure the angles between them and compare them to ones on Earth. These are the kind of things that form just in a few days when a layer of mud that has not completely turned into rock yet dries up when it sees the sun for a few days and dries out. So I think this is kind of amazing that, we're talking about things that occurred 3 or 4 billion years ago that lasted millions of years, but this is something that took just a couple days on Mars to form, and it's there for us to look at. So now we've drilled 23 drill holes and driven about 13 miles and climbed about 1,200 feet. So we every day is sort of a balance between driving and sampling. Every drill hole takes us about a month, and we also want to climb the mountain. So we're constantly battling on do we drive today? Do we stick around and drill this place? Having to really prioritize what we do. But 23 drill holes is we've probably spent about 2 years of our life drilling, and about 5 years of our life driving, and we're really making progress climbing this mountain. Another thing you can see here is the nature of the rock really does change from place to place. And one of the striking things is that the red color of Mars isn't universal. So one of the, some of the drill holes are distinctly Martian red. The iron oxides in the minerals give it that red color. And some of the other drill holes, especially when you get below the dust that coats everything on Mars, that is red, are gray. They're unaltered basaltic minerals that have not been oxidized, even though they've been just a few microns away from the surface of Mars. Once you drill into the rock is fairly pristine. And that is really good news for missions like the 2020 rover that are going to search for evidence of ancient life. Because one of the things that will happen when the oxidation is more pervasive into the rock is you can destroy the organic molecules, that evidence of life that may have been left in those rocks. Speaking of destroying organics, another discovery we had last year was now that we've discovered more and more organic molecules, we've still discovered mainly kind of simple ones. We're hoping to find some nice big ones like approaching amino acid size. That would be pretty spectacular. But we've so far found relatively simple ones, but one thing we found that they have in common, they have an overabundance of sulfur in them. And we think this is because sulfur is something that can strengthen an organic molecule and make it more robust to degradation over time. And so you can see this simple organic molecule with a sulfur bond that maybe toughens it up. And for example, Mr. Goodyear, who figured out how to make rubber strong, learned how to make sulfur interact with organics to create more resistant rubber. Yeah, vulcanization, exactly. Another thing that we study that is of interest just by itself, it's interesting, even if it has nothing to do with life, but also interesting in the case of maybe a hint of modern life on Mars today is the methane cycle. So just in the years before Curiosity arrived, astronomers on Earth using Earth-based telescopes started seeing clouds of methane, or plumes of methane, I should say, in the Martian atmosphere. Very small trace amounts, but something you could measure from Earth, and it seemed to shift with season and only be in one hemisphere and not the other. This was all very mysterious because really methane on Mars is thought to be destroyed very quickly, should only last 100 or 200 years. So why would it be there, for one thing? And once it's there, actually, if it lasts 100 years, why should it vary from place to place? It should just kind of be constant everywhere. So this was a mystery. So actually, we had a very late addition to Curiosity to add a sensor to study methane in the Martian atmosphere. And we landed there, and we didn't see anything for a while. And then we saw a big spike in our readings, still very trace amounts. Went from basically 0 to about 6 parts per billion. So every billion molecules had 6 methanes in them. That's about the amount of methane. But then it went away. So we saw one of these spikes of methane. Then we figured out how to make our experiment about 20 times more sensitive. And once we did that, we began to see methane every single measurement. And in fact, as we did that for a few years, we saw that there was a seasonal cycle of methane at very low levels, about 1 part per billion of the atmosphere. And this is that spring, summer, autumn, winter. This is that seasonal cycle of methane. So now we've seen a seasonal cycle that is repeatable year to year. And on top of that, these spikes that still seem to happen, about 6 parts per billion, 10 parts per billion. In June of this year, we saw a spike up to 20 parts per billion. And we have really no explanation for the spikes. The seasonal pattern, we have an idea that it could be caused by slow seepage of methane from underground that is kind of throttled at the surface by the seasonal temperatures. So it comes out more in the spring and summer and less in the winter and fall. But generally, it's being produced by some activity underground, either natural geological activity, which can produce methane, or, and this is much more less certain, or even modern biological activity. And another pretty picture. We discovered, for years, we didn't see any clouds. And as you probably know, Spirit and Opportunity, the rovers before Curiosity, saw lots of clouds. So it was a little bit of a mystery why we didn't see any clouds at our landing site. But just recently, we'd been looking in the middle of the day, which is when you think you might have the best chance of seeing clouds. For years, we didn't do this, but then we started looking right at sunset and after sunset. Not the ideal time to look for clouds, you might think. But there are certain type of clouds called noctilucent clouds that are best observed right after sunset when the sky is dark, the sun is over the horizon, but still able to light up the clouds from the bottom. And so that's what these are. These are noctilucent clouds on Mars, very high altitude clouds. Same with noctilucent clouds on Earth. They're rare, very high altitude clouds that light up in this way when the sun is just over the horizon. And so these are either water ice or carbon dioxide clouds. We're trying to figure that out. And they're just really pretty. Okay, so kind of wrapping up, Mars was once wet. Was it warm? We think it was, and the reason we think it was is I told you all the evidence that we've gathered with Curiosity for how long the water lasted. These lakes lasted for many years to form all those fine layers, and then the water flowed again through all those cracks, forming the veins. To do that, you really need persistent water, and to have persistent water, it can't just be a trickle that melts from ice every year if Mars is cold. It can't be an ephemeral amount of water from a comet impacting once every 10 million years. We think there was a hydrological cycle, rain falling, streams flowing, and that lasted for quite a long time. That's controversial, by the way. We still need to figure out how that happened, but that's certainly where we think the evidence is pointing with Curiosity. And was it habitable? Tens of millions of years at least, we think is what's required to build up all those layers and to have those water forming the veins. And that's getting to be the amount of time that is biologically relevant for evolution to make use of. Last slide, 2020 mission's coming up. It looks a lot like Curiosity, and I'm not sure you have a speaker about it, so I'll just say a little. But the 2020 rover is based on the same overall architecture of Curiosity, the 6 wheels and the same body, same mast, same similar arm, but the payload is quite different. It has instruments that are not designed for habitability, but for actually looking for patterns in the mineralogy, the chemistry, that indicate past life. And so it has some very high resolution ability to look at the chemicals and the minerals in the soil and rocks. And it also does a very important task, which is to take cores, intact cores. We drill and grind into a powder. 2020 will take intact cores and put them into a tube and seal the tube and collect a few dozen of these sealed tubes and leave them for a future set of missions to one day return to Earth. So 2020 will be the first time since Viking that we're directly looking for life on Mars, and also bringing, first time ever, that we're bringing material back to Earth to study with much better laboratories than we could ever send to Mars, and really hopefully answer once and for all if Mars ever hosted life. Thank you very much.
Mission to Mars 2020 for the next decade, what instruments would you like to put on it that we haven't been able to send up there yet? And is there any particular place where you would like to go where we haven't been there yet?
Yeah, good question. I think at this point, a lot of the Mars community is thinking it's better to bring the samples back and use much wider variety of instruments and better instruments than we could ever send. So I think I'll take a little bit of a turn to the answer and say, probably we're, better than sending any more astrobiological instruments. Let's bring samples back. But what we haven't done, because we've been really focused on landing sites like this to look for evidence of ancient life, we haven't really explored modern processes that well. We haven't been to the polar caps. And the polar caps are really interesting places because that's where the water is today. That's where the evidence of modern climate change, there's ice ages going on Mars currently. I think it's been somewhat neglected. I would have said the interior has been neglected, but we finally have the InSight lander now that is doing seismology. So as we focus on studying life, we also need to understand Mars as a planet, which includes things like the modern ice ages and the interior of the planet.
Two questions. 3 billion years ago, the sun was presumably about 25% cooler. Do we see any evidence of snowball Mars? Are there any signs of, let's say, U-shaped glacial valleys or moraines? And also another question, about 10 years ago, I talked to a JPL engineer about Rover, the Spirit and Opportunity and the limitations of those, and there were 3 of them he indicated. Number 1 was power. The thing had to move along at about snail's pace maximum. Number 2 was the deep space network that you only talk to it about twice a day at best. And number 3 was, even though they could do autonomy, the managers at JPL refused to allow them to do it because they're so scared of crashing the thing off a cliff. Yeah. Has that improved?
Every one of those has improved. Probably the autonomy and the driving less than you might think, and there's some reason why I still think that's probably the right idea. We want to be very careful how we drive a $2 billion laboratory around. And autonomy, we use it where it is valuable, and I think we're doing more and more of that with Curiosity. But also as a scientist, we don't want to make everything autonomous. It's very important for scientists on Earth to interact with the rover on a daily basis and pick every target very carefully to do the best quality we can, work that we can. And another reason why astronauts on Mars will help with that as well. Now, quickly answering your other question, there are evidence for glaciers on ancient Mars. There's evidence that ice ages today have glaciated the equator even recently as well. The thing that you mentioned about the faint young sun, 75% of its current luminosity in the past, that's what makes it hard. That's what makes it controversial that we're saying it rained at Gale Crater. There's no climate model that produces rain at Gale Crater right now because of the faint young sun. So we have to solve that paradox.
Last question.
Yes, I noticed we're looking at like roughly 5 kilometers of layered sediments.
Yep.
That's a very thick layer of sediments even for Earth standards.
Yes.
But what we also notice from the picture, it's all bright red. It looks like it's highly oxidized. Can you comment on that?
Yeah. So there's. Thank you for pointing out how thick a package of sediments is. That's what makes it so exciting, and what makes the time scale so long.
Yes.
Now that we found that 1,200 feet of it, at least, because that's how high we are now, all formed at the bottom of an ancient lake, a series of lakes, I should say. So that's a lot of lake sediment. The other point about everything being red, so at the surface, everything is because of all the dust that coats everything. And as some of those drill hole pictures showed, once we get below that veneer of dust, there is unoxidized rock in places. But sometimes groundwater has permeated the rocks and oxidized everything. There are little islands where that hasn't happened, and that's where you want to return samples back to Earth.